Hello, everyone. We're at Massaw Engineering. We approached the Eastern Municipal Water District for the reservoir site design. My name is Brian Steeman. I'm the project manager.
Hi, my name is Tyler Abel.
My name is Mustafa Abdulwahid.
And my name is Blake Morton.
I want to talk to you a little bit about what we're going to be talking about today. We're going to bring up the background of this project, look at some of the problems and challenges that we saw when we were looking at this project. We'll walk you through some of the studies that we did, as well as finally looking at the solution, our overall site design, as well as the project lifetime sustainability and costs associated with this project. So talk a little bit more about what we're doing here. Eastern Municipal Water District is a water district in southwestern Riverside County who currently operate about 80 water reservoirs. These are anywhere from 3 to 4 million gallons. We'll be doing a site civil infrastructure design for a 4 million gallon reservoir located in southwestern Riverside County near Menifee. And again, the tank will not be included in this design. This will be just looking at access road, ring road, and site civil needs such as storm drains, water mains, etc. Specific to this project, each water tank that EMWD is doing requires a high water level. And this tank's high water level is 1,720 feet. So typical tank diameters are shown on the screen, and these are going to lead to an elevation, which is going to be 1,690. So that's a location that's going to be important on this hillside to be looking at because we need to be at that elevation for an effective design. Furthermore, below this hillside, there's some homes below, and we have to think about the community impact when we're doing the design for this project. So I'll pass it off to Blake to talk a little bit about the challenges of this project.
Yeah, so some of the challenges on the project was one, there were some radius issues when we were designing the access road. There's also challenges due to the terrain of the hillside that the access road was going on. There are also visual impacts to placing the tank and the access road on the side of the large hillsides. There's also issues addressing sustainability due to the product not being fully complete. And the type of soil on the project site also presented a challenge due to runoff. So some of the studies we performed for this project were access and ring road studies. We also did hydraulics and an electrical study. We performed hydrology study, storm drain study, and also created a site logistics plan.
Moving into the hydrology study, the first thing we identified was that our site's located near a tributary to Lake Elsinore. That is Salt Creek, which you can see outlined in purple, with the floodplain area. This can present a big risk for debris runoff going into the drinking water, as well as other pollutants, as well as a flood risk for surrounding communities. So it's really important that we keep all the water that comes off of our site contained. In order to know how much is coming off of our site, we use the Riverside Hydrology Manual and the rational formula to get a total discharge, which is the total cubic foot per second of water coming through our site during a 10-year and 100-year storm event.
So I'll talk a little bit about how we set our access road. So all of the design criteria that we are using were at the very minimum for Eastern Municipal Water District at the least. We also exceeded some of their standards. Some such standards include that our maximum slope was 12%, whereas the maximum slope required was 15%. We ended up designing a road that is about 2,500 feet long with 200 feet of elevation change that follows an existing fire road that you can see there at right. And I'll pass it back to Tyler to talk about the storm drain study.
So we're going to kind of see a similar process to what we did in the hydrology study, the storm drain study. We're going to determine the peak discharge from a tank overflow event using the rational formula again with a pipe diameter of 24 inches and a velocity of 2.5 feet per second. We're then going to add this discharge to the original discharge we got for a 10-year storm. For us, this came out to about 20.41 cubic feet per second, and then we're going to use this to eventually determine the sizing for our culvert. We kind of worked backwards with standard size culverts and our total discharge in order to determine the velocity of the water that we felt would be appropriate for our culvert. We ended up settling for a 2x4 culvert with a water velocity of 2.55 feet per second.
So getting into the geotechnical study, there are no active faults that traverse the project site. However, there are other faults nearby that may impact the project. A number of materials were encountered when we were exploring the project site. And after our explorations, we determined little potential for settlement due to us not encountering any water. And for the pavement design of the access road, we based our design off of the AASHTO pavement design manual and ultimately we came up with a design of 4 inches of asphalt over 6 inches of Class 2 base.
For the site logistics plan for the project, we use a 3D modeling to illustrate the site logistics, and we'll have 5 phases. And this, what is shown on the slide is have a general look for the site logistics and where's the reservoir going to be located. And now I'm going to turn it to Tyler.
Yeah, so now we're going to do a little summary of the solution to the overall site design. The access road is going to follow the existing fire road. This is going to limit the amount of grading we'll have to do to put that in. The storm drain is going to parallel this access road. This is to limit the amount of slope and water velocity. We're going to keep it to about 10% by following the road. And again, we're going to use a 4x2 closed culvert to provide constructability and protect from flood events that are unpredictable, keeping that over the top protection. Furthermore, the water main and the electrical conduit are going to take a little bit of a different approach, but they're going to be installed together to limit the amount of work done there. The storm drain utilities are going to tie into the existing Ridgecrest road facilities, so those will not have to be reconstructed. This can improve constructability, cost effectiveness, decrease the amount of time spent on the project during the construction phase, and reduce the community impact.
Project lifetime is uncertain because the tank is not included in the scope of work. And for the sustainability, is the solar panel in the future can add to the efficiency of the project, and also the existing infrastructure for in the location is going to decrease any environmental impact. And for the cost, the detailed cost, construction cost for the project is going to be $10 million, as going to be shown in the next slide. So the cost is going to be estimated between the general condition, the heavy equipment for the project, the hard and soft cost, the permits, and the contingency of the project. And as shown the slide, is going to cost around $10 million for the project.
And with that, we're going to conclude. Thank you, everyone, for your interest in our project and for listening.